And the answer to the second question is also yes. Groups of intermediate growth were constructed by Grigorchuk. I already mentioned his counterexamples to the Burnside problem. The same examples had intermediate growth. Now, let us talk about the strongest form of fast growth, the so-called property tau. And I have to start in what is now referred to as the theoretical computer science. Let gamma be a finite connected graph. So V is a set of vertices, E is the set of edges. If W is a set of vertices, then the boundary consists of those vertices that do not lie in W, but that are connected by a simple H to some element from W. So if there is an expansion, say, of a current, from W it goes to the boundary, and so on. The following definition is due to Pinsker. Let epsilon be a positive number. Epsilon can be only a positive number. A finite connected graph gamma is said to be an epsilon expander if for any set of vertices, well, which is not too big, say less than 1/2 of all elements, if you add the boundary, then the size will expand at least 1 plus epsilon times. That is the rate of expansion. Think of all these vertices as electric nodes, and then say you put current, electric current to one of them, then it expands from that node, from a subset to its boundary and so on, and 1 plus epsilon characterizes the rate of expansion. Well, but then every finite connected graph is an epsilon expander if you choose epsilon sufficiently small. That's not interesting. In fact, what is interesting, we are interested in an infinite family of epsilon expanders where epsilon is fixed. Also, we want all these finite connected graphs to be k-regular, where k is fixed. K-regular means that from every vertex there are exactly k edges adjacent to that vertex. So we want k to be fixed and epsilon to be fixed, but the size goes to infinity. Well, it seems that this is becoming a very applied notion. It is used a lot in network design because in this way we get highly connected graphs cheaply. Of course, the best graph is a complete graph where all vertices are connected, but that's expensive. And here, talking about graphs, the size goes to infinity, but they stay k-regular, relatively cheap. And the rate of expansion is good. 1 plus epsilon, because epsilon is fixed. So, we want the families of finite k-regular epsilon expanders, where the size goes to infinity. Pinsker and independently Erdős proved that random k-regular graphs provide with such family. But they wanted an explicit construction, which could be really used in algorithms. And in computer science, explicit means that you construct the nth member in polynomial time. The first such construction was suggested by Margulis. It's because he knew functional analysis. In 1967, Kazhdan made the following very important observation. He noticed that some groups are finitely generated and there exists some positive epsilon such that for any unitary representation in a Hilbert space H, so a homomorphism from the group to the group of unitary operators, without non-zero fixed points, if you choose a non-zero element H, then at least for one generator, that generator moves that element significantly compared to the length of the element. You know, if you choose a non-zero element, then at least one generator moves it. Otherwise, it would have been a fixed element. But it moves it significantly, epsilon times the length times. And remark that it is universal for all unitary representations. For example, the group SLNZ, so the group of integer matrices, n by n integer matrices with determinant 1, where n is greater or equal than 3, has that property. He called it property T because by that time in functional analysis there was property S, so it was just next. Now, Margulis made the following observation. If G is a residually finite group, and it has property T, for example, SLNZ. Okay, then let us fix some generating set, X. And if Gi is a finite homomorphic image, then a generating set, of course, is mapped to a generating set. And if you have a group and you fix a generating set, you could consider the so-called Kelly graph. The vertices of that graph are of the group, and are connected by a simple H if one element is equal to another element times some generator. So you get a connected graph. So Margulis noticed that these families of finite connected graphs, and by the way, they are K-regular, K is equal to the number of generators, is an expander family. Why? The proof takes 2 lines. I will do it by waving hands. What do we need to prove? We need to prove that if we choose a finite subset and add the boundary, then it moves, it increases significantly. Let's consider the characteristic function of that finite subset. You know, the group G acts on homomorphic images. Hence, it acts on functions. It acts on the argument. For a set to be moved significantly means that the characteristic function changes significantly. But the group G has property T. The end of the proof, almost. Okay, but so a group, if a group G is residually finite, and you have just translated to a different language, period. If a group G has property T and residually finite, so we get this expander, family of expander graphs. But sometimes you get this family of expander graphs, but the group did not have property T. So this is a weak property. And Lubotsky and Zimmer called it property tau. Tau is a small t. So T implies tau. The reverse is not true. Now let us talk about counterexamples to the Burnside problem that I mentioned before, about the construction of Golet and Shafarevich. Once we have a free pro-P group, we can define groups by generators and relators. So let R be a subset, and let us consider the closed normal subgroup generated by that subset. Since what we have in mind is to factor it out, it's not enough to consider the normal subgroup. In topological groups, it's legal to factor out only closed normal subgroup. So we consider the closed normal subgroup, we factor it out, and we say that this group is presented by the generators x1, x2, and so on, and by the set of relators R, in the category of pro-P groups. Well, just with all presentations, as with all presentations by generators and relators, it's very difficult to say anything about a group by generators and relators. There doesn't exist an algorithm that would allow you to decide if this group is an identity group or not, finite or infinite. But Golet and Shafarevich found a sufficient condition for a pro-P group presented by generators and relators to be infinite. I won't formulate this condition in full generality. I will formulate only an important particular case, which is not enough to settle the Burnside problem, but which is interesting for different reasons. They proved that if all our relators lie in the Frattini subgroup, that is the subgroup generated by piece powers and commutators, and if the number of relators is not big enough, less than m squared divided by 4, where m is the number of generators, then the group is infinite. And the first assumption may look strong, but it's very natural, because if some relator does not lie in the Frattini subgroup, it just means that some generator can be expressed by other generators. We don't want it. So the proof takes one page also. It was important to notice it. And immediately they used this criterion in a powerful way. Shafarevich solved an old problem. He constructed an infinite tower of class fields because he was able to estimate the number of relators in the Galois group. It was less than m squared divided by 4. So the group was infinite. So the tower was infinite. And Goddard used it to construct a counterexample to the Burnside problem. He defined it by generators and relators, but then how do you prove that the group is infinite? Okay. In the year 2000, I proved, well, even before, but published in the year 2000, that a group which is infinite because of the Golod-Shafarevich criterion, I will refer to them as Golod-Shafarevich groups, are not only infinite, but they are very strongly infinite. They contain the free propy group, non-abelian free propy group. And now I want to consider two examples of Golod-Shafarevich groups. You know, initially Golod-Shafarevich groups were interesting as counterexamples. Later, there appeared better reasons to be interested in these groups. The first example is due to Shafarevich. Let S be a finite set of primes which does not include P, and the order of that set is M. Let K be the maximal pro-P extension of the rational numbers, and pro-P extension means that the Galois group is pro-P, which is unramified outside of S. Then the Galois group, as a pro-P group, has the following presentation: M generators and M relators, and every relator is some piece power of the generator is equal to some commutator involving the generator. This is a pure existence theorem. I don't think that there is a single case when this presentation could be written down explicitly. But it is clear that all relators involve only piece powers and commutators. Hence they lie in the Frattini subgroup. The number of relators is M. If M is greater than 4, then M is less than M squared divided by 4. So the group is infinite by the Golod-Shafarevich theorem. So this is the Golod-Shafarevich group. Another example. Let X be a compact hyperbolic 3-manifold and gamma is its fundamental group. Then for almost all primes, almost all means all but finitely many. This fundamental group has a subgroup of finite index whose pro-P completion is Golod-Shafarevich. By the way, when speaking about a discrete group, I will say that this is a Golod-Shafarevich group if its pro-P completion is Golod-Shafarevich. So it is also infinite, because if a pro-P completion is infinite, then the group is infinite as well. That was an observation of Lubotsky. Well, in '83.